Hey everyone, and welcome. Today, we're diving deep into something that's happening billions of times a second inside your computer, arithmetic. But this isn't going to be a math lesson, I promise. We're going to look at how CPUs really do their calculations. And what you find is this amazing world of clever design, tough constraints, and what it all comes down to, the art of the trade-off. All right, let's just jump right in with a question. Registers are the absolute fastest memory you can get inside a CPU. So why don't we just, pack 1,000 of them onto a chip? It seems like a total no-brainer for getting a huge boost in speed, right? Well, as you might guess, there's a catch. And boom, here's the catch. This one quote gets right to the heart of everything in CPU design. It's not about having unlimited power or space. It's about making every single bit count. That real estate on a chip is unbelievably expensive, and adding more of anything always has a price. So let's talk about that price. Let's really try to understand what it actually costs to add just one more simple component, like a register, into our grand CPU design. Okay, here's the math, but stick with me, it's pretty simple. To tell the CPU, hey, use that register, you need a unique address for it. And that address has to be embedded inside every single instruction. So, with 32 registers, like in the classic MIPS architecture, you need log base 2 of 32, which is 5 bits, just for the address. Now, what if you double the registers to 64? You now need 6 bits. That might not sound like a huge deal, but that one extra bit has to come from somewhere else in the instruction. You're stealing it from other parts, which can limit how complex your operations can be. All right, so now that we've got this idea of cost in our heads, let's see how it plays out with the most basic operation of all, just adding two numbers. You're about to see that even here, the trade-offs are absolutely everywhere. Let's do a little thought experiment. You're the designer now. It's your job to build a circuit that adds. What's the most straightforward way you can think of? Well, it's probably the same way you learned in first grade, right? Add the first column, write down the sum, and carry the one over to the next column. And that's exactly what this circuit does. It's called a ripple carry adder, and it's beautiful in its simplicity. It's cheap to build, easy to understand, but it has one massive hidden flaw, a flaw that makes it pretty much useless for any modern fast processor. And this right here just nails the problem perfectly. That flaw is all about speed. You see, each little building block in that chain has to wait for the result from the one before it. That little carry signal has to literally ripple all the way from the first bit to the very last bit. For a 64-bit number, that's an eternity in CPU time. So the whole challenge becomes a race. How can we possibly get the final answer without sitting around and waiting for that painfully slow carry signal to make its way through the whole circuit? This is where the real genius of CPU design starts to shine. Think of the ripple carry adder like a long line of dominoes. You simply can't know the final result until the very last domino has fallen. So what's the solution? Well, instead of waiting, the smarter adders use some really complex logic to look at the two numbers coming in and predict what the carry is going to be for each bit, basically all at once. It's like turning a one-lane country road into a multi-lane superhighway. And this slide just shows you the trade-off in plain sight. On the left, there's our simple, clean, but slow ripple carry adder. And on the right, whoa, look at that thing. That's a carry look-ahead adder. The difference in complexity is just staggering. That circuit on the right is way faster, but it takes up a lot more logic, more power, and more of that precious chip real estate we were talking about. And carry look-ahead is just one way to crack this nut. Engineers have come up with all sorts of other brilliant solutions, like carry skip adders and carry select adders. Each one has its own clever little way of balancing speed, cost, and complexity. Okay, so if just adding two numbers is that complicated, you can probably imagine that multiplication and division are a whole other can of worms. Let's take a look at how these same ideas, clever shortcuts and trade-offs, apply here. For multiplication, one of the really elegant tricks is something called Booth's algorithm. Instead of just doing addition over and over again, which is slow, it scans the bits of one of the numbers and makes smart decisions. It knows when to add, when to subtract, and, this is the real key, when to do nothing at all and just skip a whole bunch of work. Let's just quickly walk through this example of multiplying -6 by -5. The algorithm looks at pairs of bits. Check out step 1. It sees 0, 0 at the end of the bits, so it just does nothing. It just shifts. No expensive addition, no subtraction. That's a skip. Now look at step 2. It sees a 0, 1 pattern, and that tells it to add B.
Then in step 3, it sees 1, 0, so it subtracts B. It's this intelligent ability to add, subtract, or just skip based on the bit patterns that makes it so much faster. And then there's division. Division is even trickier. And here, again, the designer has a big choice to make. Do you build a circuit that plays it safe and careful, or do you build one that's a bit more aggressive, more complex, but hopefully faster?
So you have these two main methods, restoring and non-restoring division. You can think of restoring division as being super cautious. It subtracts, and if the result ends up being negative, it goes, oops, my bad, and it adds the number right back to restore the value it had before. Non-restoring division, on the other hand, is the risk taker. It subtracts, gets a negative number, and just says, fine, I'll just roll with this negative number and fix everything at the end. It's more complex for sure, but it often gets the job done in fewer steps.
And the key is right there in step 2. The algorithm is always pushing forward. It either adds or subtracts, depending on whether the partial remainder is positive or negative. It never, ever has to go backward and do a restoring step. It doesn't waste clock cycles undoing its mistakes, and that's what makes it faster. Take a look at this quick example of 14 divided by 3. See what happens in that third row? After the first subtraction, the result in register P goes negative. The restoring algorithm would now burn a whole clock cycle adding 3 back. But the non-restoring one, it just sets the bit to 0 and keeps on trucking. Later on, it knows to do an addition instead of a subtraction to make up for it. It's a more complicated dance, but by not undoing that step, it saves time. So from the number of registers we choose to how we add, how we multiply, and how we divide, we keep coming back to this exact same idea, this one central theme. This is it. This is the fundamental battle that rages at the heart of computer architecture. Every single decision is a negotiation. You want it to be faster? Great, but it's going to cost you in complexity and chip area. You want it to be simpler and cheaper? No problem, but you're going to pay that price in performance. There is no free lunch. And this is really the main thing to take away from all this. The true genius of modern processors isn't just their incredible speed. It's in the thousands of brilliant, elegant compromises made by their designers. It's all about finding that perfect, practical sweet spot between the simple solution that's just too slow and the super fast solution that's way too expensive or complex. Finding that balance, that is the art of great engineering. So the next time you hear about a new M-series chip from Apple or a new core processor from Intel, I want you to think about this. What invisible, incredibly complicated trade-offs did the engineers have to wrestle with deep down in the silicon to get that performance? What races did they decide to win, and what price did they have to pay to win them? Thanks for joining me.